Okay, so this talk is about mercury in the environment. The first part will be my work with the United Nations Environment Program on the global mercury assessment for the last 5 years, work supported by EGP, and then the second part is a couple of individual research papers that I think illustrate nicely the complexity of the mercury biogeochemical cycle in the environment. Next, please. So the elements of the UNEP assessment, there were a lot of people involved in the GMA 2018, as there was in the 2013 assessment, and the goal of this assessment was to start a 5-year regular recurring assessment process, which would evaluate the state of mercury science globally, but also provide guidance for how to monitor the Minamata Convention on Mercury, which was ratified by Canada and over 100 other nations in 2017, which is now in effect, the goal of which is to reduce mercury emissions into the environment and reduce mercury exposure to people through food and other sources. I was involved with a variety of colleagues on 2 chapters. We were called the Aquatic Geochemistry Team, for want of a better word. This report is currently in press. It was supposed to come out in 2018, but there are a number of different chapters, 9 I think in total, and 1 or 2 are a bit late, so the whole report is held up. Next, please. By its nature, this sort of global multinational assessment involves people from a lot of different countries, and you can see them listed there. The key ones are Fei Wang from the University of Manitoba, Rob Mason from the University of Connecticut, Xinbin Feng from China, Hamid Sinai from Denmark, and Sol Guerrero from Venezuela. They were key in a number of different elements here. And the Arctic Monitoring Assessment Program, who I've worked with a lot over 20 years, they actually were managing the whole process for the United Nations, and they do that sort of work quite a lot. Next, please. The whole assessment goes through 2 rounds of quite intense review. One is as an anonymous peer review, which had up to 6 anonymous science peers reviewing each chapter. The second was every nation that signed up to the Minamata Convention had the potential to comment on the draft chapters, so we got comments and revisions from both of those. And then we were also strongly encouraged to submit each of our chapters for journal peer review, because it's important that national governments around the world have confidence that the work that they see is actually supported by the scientific community in general. And this is the output from the second chapter of the upcoming assessment on the global budget and cycle. Came out late last year. Next, please. I'm not going to go through all of the findings, all of the numbers in this sort of summary plot of the global cycle. You can look at this online if you want to. And there's not a lot of surprise here. There wasn't a lot of change from 2013. For example, we think that anthropogenic sources this year are putting in about 2,500 tonnes or 2.5 megatons into the year. We have enough confidence on that number to assign an uncertainty range of 2 to 3 megatons per year. And then that's about 5 times higher than geogenic sources, which we think are around about 0.5 megatons per year. What I really want to talk about a little bit is the uncertainty that is involved in around these numbers. And mercury is one of the most difficult and complex of metals to work on, mainly when you get right down to it because of its redox chemistry. Mercury found in soils and waters, lakes and oceans, it can be in the elemental form, Hg0, it can be in ionic form, Hg2. Hg2 can be photo-reduced back to elemental mercury, and that's volatile. So there's a lot of mercury going from surface oceans and soils into the air. And in the air, Hg0 gets photo-oxidized to Hg0, which then deposits very rapidly back to soils and oceans. So you get this repeated rapid and more or less endless cycle of volatilization and deposition. Two implications from that. One is that mercury emitted from anywhere on the surface of the planet can be transported as gas to anywhere else on the planet and deposited. And secondly, that historic emissions, not just this year, but historic emissions, are still circulating in the biosphere and the geosphere because the removal rate into deep ocean sediments and mineral soils is extremely slow compared to the rate of mobilization. And the natural sources are a particular source of uncertainty here because of the amount of, well, the very limited amount of work done on natural sources in general. Next, please. So that's one chapter. And the second chapter we worked on, chapter 9, was something about how do you go about monitoring the effect of the convention. And some suggestions from some nations would have us measure one keystone species like tuna in the ocean, for example. And we wanted to look here in this chapter about how closely mercury trends in fish and other aquatic wildlife that people eat, and it's their major source of mercury exposure, how closely they track those in the atmosphere. Next, please. So we looked at 4 regional case studies, the Arctic, North America, Europe, and China. And we found in the past few decades, that oftentimes these trends are not related. And the overarching explanation for this is climate change, but there are a number of different sort of sub-factors that are related to changing environmental biogeochemistry, which get in between, if you like, the atmosphere and uptake into food chains. And then in food chains themselves, there's a lot of biological, ecological factors that change the rate of uptake and transmission to higher levels of food chain. There's one example on the left there in Lake Superior, 2 different sites. You'd expect it to have the same atmospheric deposition rate. One species, the herring gull egg, shows a constant decline, which is similar to the atmosphere over the last 40 years or so. And then the other species that we looked at, lake trout, showed an initial decline and then a flattening off, and now a recent increase for reasons we don't understand, but are clearly not related to air trends. So we developed this sort of, diagram on the right there, which tried to make the point that we're now entering a different phase of mercury in the environment where we're no longer controlled by, or mercury in the environment in biota are no longer controlled by emissions. Rather, it's the processes in the environment that are changing that. And that means that in the future, the trends, even with reducing emissions into the environment, trends in biota will be essentially unpredictable, and there'll be a range of outcomes ranging from a proportional and rapid decline to virtually no decline at all. And we hope that will guide deliberations at UNEP about how to best monitor Minamata Convention. Next slide, please. So very quickly, my own individual research, I just wanted to show very quickly a couple of process-related slides. Here we're looking at algal scavenging of mercury in Arctic lakes, pre-industrial Arctic lakes. One example of how changing one aspect in the environment can change what you see in one of the matrices, in this case lake sediments. The take-home message is here that similar to what Martine alluded to, that organic matter, particularly algal organic matter, affects natural baseline mercury concentrations and fluxes in lake sediments. That's been proposed before by our research group and had a lot of pushback from environmental chemists from certain places, but this is a pretty definitive study, we think. The implication is that calculating anthropogenic fluxes in the 20th century needs a rethink because the natural baseline is changing over time. Next, please. And the last slide concerns another study on one of the same lakes that we looked at in the previous paper. That over 7,000 years, we showed that over 7,000 years, it's not algal productivity that's most important, it's actually changing air temperature during the Holocene, which impacts erosion rates in this carbonate terrain, and that dilutes the major element of calcium, dilutes all of the other elements, including mercury, over that period of time. It's only in the last millennium that algal scavenging becomes dominant. Next, please. So my last slide is the contact info. Thank you.
Thank you. Thank you, Peter.